Okay, I can see myself. Mm, okay.
Can you hear me? Can you hear me, Mark? Yeah? I'm not hearing you live. Oh, you're still muted on Discord. Can you hear me, Mark?
Yes,
Yeah?
very loudly.
I'm not hearing you live.
Yeah, I think I can hear you on the slight delay.
Yeah, I just put it on. I just pulled the YouTube video up too. Can you hear me, Mark? Okay.
The challenge here to switch this. Can you say something really quick just so I can check? Okay, I can still hear you. Yeah, can you hear me? Okay, cool. That means that my computer won't be able to pick up the audio that's going into my headphones, which is good. Yeah, I can. Awesome. Sure. So the topic today is reduction and what that means, what that entails. And the place to start is what kilns do and what types of kilns there are. So the most common type of kiln now is an electric kiln, and it works just like an oven. You have nichrome coils inside that you put electricity through, and they heat up, and it heats up the environment. But there's plenty of oxygen, and there's no flame. So there's essentially no environmental impact on the clay itself when you fire in an electric kiln. It's just going to do what it does naturally in a sort of clear environment inside the kiln. And mostly those are used for bisque firings. So if you fire your pots first time, it basically makes them safe to glaze and gets out any organic materials. And then you can fire them a second time with glaze on them, and that's where you get a choice between oxidation or reduction, or just what kind of kiln you want to fire them in, because you can do pretty much anything at this point. But there are certain reasons to fire in reduction, which we'll get to. So the way you fire in reduction is by using a fuel kiln. So a kiln that uses some combustible fuel, whether that's gas, oil, wood, coal, and you're introducing the flame with that fuel. I think that should bring us into the next slide. In a fuel kiln, you end up with what potters call atmosphere. So you either have sort of a smoky atmosphere where there's a lot of fuel inside the kiln, or a clear atmosphere where there's not much fuel inside of the kiln, and you have sort of an efficient burning. Um, let's see. Okay, yeah. So naturally, an electric kiln is going to be an oxidation. Naturally, a gas kiln is going to be in sort of a mild reduction. Just because you have fuel introduced into the environment, there will be a little bit of reduction inside of the atmosphere. And that should bring us forward a little more. Yep, covered that. Okay, so basically in a gas kiln, you can either have an efficient firing of the flame through the kiln, or you can add more fuel than the kiln can efficiently combust, and that's when you get a sort of smoky atmosphere, and you start to reduce inside of the kiln. Crude oil is another type of kiln where basically you're just shooting oil into the kiln and it's being lit as it flies in. Used commonly. Mm-hmm. What you might have been looking at might have been some sort of industrial drying kiln. For pottery kilns, usually it just looks like a spray nozzle. And so you would heat the kiln up first with like a small fire, and then you light the oil as it's being sprayed, sort of aerosolized into the kiln or dripped in, and then it burns in sort of a reservoir where it drips in. And that's usually how they work. Once it gets hot enough, though, it'll burn as it goes into the kiln, and it's more aerosolized. Yeah. So yeah, wood kilns are kind of a special case, and it's more or less the reason why potters want to reduce inside of a kiln environment, and it's because when you introduce wood, as the wood is burning, you're sort of the first thing you get is all of the liquids inside of the wood that are burning off, and that causes a very turbulent and smoky kiln atmosphere. And when you have all of those different chemicals that are going through the kiln and not just the heat of flame, you get a lot of reduction. So it's a lot of ionic interaction and oxide interaction between the clay and the glaze and the atmosphere of the kiln. And then once all of the organic materials and all the liquid materials burn out of the wood and you just have charcoal, that's when it's sort of creating a clean heat. But as that happens and there's no more sort of raw fuel inside of the wood, you have to stoke more wood. And so wood firing cycle. So it'll be reducing, oxidizing as you stoke, and then wait for it to clear, and then stoke and wait for it to clear. So if you have a pot sitting on a shelf in a wood kiln just out naturally exposed, it's always going to get reduction. You really like that control in a wood kiln is, do you want to reduce a little bit or do you want to reduce a lot? So it's really only those two options. So here I'll stop. Do we have a slide for the chemical makeup for iron? Because that's really like the meat and potatoes of what reduction is. Okay, so I'll just talk about that. So when you say reduction, I say that, and I say it means introducing too much fuel to the environment. And that's really what reduction is. It's just adding too much fuel to the environment. But the chemical sort of phenomenon is that you're pulling oxygen molecules away from the wares inside of the kiln, and it's changing what the oxides are doing. So you start with red iron oxide, Fe2O3, and it's all in throughout the clay, and there's lots of iron in the clay. And then because there's not enough oxygen in the kiln environment for efficient combustion, it's going to start ripping oxygen molecules out of your clay. And it'll change from color, right, to this like bright brick red color to sort of this darker burgundy color. This is my Lizella, and it's a very highly iron bearing clay. So what happens is that all of the iron in the clay is interacting actively with the atmosphere, and you get a really big color change, and it's a texture change as well as a density change. So each iron molecule is turning from Fe2O3, all of its oxygen is getting stolen away, and it's becoming FeO, just ferric oxide. And that's much, much stronger of a melter than Fe2O3 is. So the effect is that it pulls away that oxygen and it makes the clay and the glaze melt much more. So all of the particles of iron stick to the particles around them, and it sort of glues and gels together the whole structure of the clay. So reduction gives you a much, much tighter matrix, a much stronger material, and much denser. And then that's really the primary reason for clay to be reducing, is that you get a much denser and much harder material as well as a beautiful color, which is obviously a draw. Mm-hmm. Mm-hmm. Yeah, absolutely. So it's like the difference between if you took a sponge and you have all of these air pockets and sort of an open structure, and then you squished it down into the tiny little bricks that you get from the grocery store where they're dehydrated and flat, right? That's a really strong little material, and it's kind of hard to work with or bend or do anything with. But then you add water to it, and all of a sudden it expands, right? The action of the iron is essentially the removal of water and space inside of that clay matrix, where it melts everything and compacts everything together. Yeah, and the reason why we want to fire in reduction kilns, in gas kilns, in a wood kiln, in a coal kiln, which is less common now, is just because you have that control. In an oxidation kiln, in a electric kiln, you always are going to end up with the same result, which is desirable because you know it's going to be the same every time. There's really no change in conditions. But with a gas kiln, right, you have to control every aspect of the firing and make sure that whatever you're doing is influencing the clay and the glaze in the way that you want it to. Yeah. Yeah. Mm-hmm. So the question is, it's difficult. So I would say it's actually more difficult to make interesting work in an electric kiln because the result is so flat and consistent. But it's definitely more difficult to learn how to fire a gas kiln than it is an electric kiln. Most modern electric kilns, you punch in a program, you hit go, and then you walk away and come back and it's done. With a gas kiln, you really have to be there all day, and you need to check in on it at certain periods. There's no like, Bluetooth alerts when the kiln gets to certain temperatures. You have to look inside of a spy hole and see when the pyrometric cones are moving and sort of do the right processes throughout the firing then that way. So it's definitely more involved. Yeah, and it's a learning thing. Hmm. Yeah, and that's a big part of industrial ceramics, right? Is trying to make things that are interesting and unique looking and handmade looking, but doing them with the most efficient and cost-effective processes. And so there are a lot of really great potters out there that can do wonderful things with oxidation fired work, where they're using spray guns and sort of spraying thin layers of different glazes on top of each other, or speckling with the spray gun. A lot of stuff with a spray gun, honestly, because it gives you sort of that atmospheric layered effect. Um, but it's a lot of work beforehand versus more work while you're firing. So it's a balance, right? With wood firing, a lot of the reason for cost is just because wood is expensive. Unless you have a place to harvest wood and you have a good source of lots of dried, cured wood, it can be very expensive to fire a wood kiln, especially somewhere like Japan, where they're bringing in apple wood from orchards and having to buy it and store it for years and have it just right dried. So wood firing is definitely the most involved, where you're literally the mechanism of fuel introduction physically. And then you have a gas kiln where you're introducing the way that the flame is shaped. You're introducing how much fuel is going into the kiln, and you're being able to adjust dampers to control sort of the environment in the kiln. And then you go to an electric kiln where you essentially just turn it on. There are no levers to turn. So with oxidation, like it says, it's pretty much standard, consistent all the way across. There are some funny things you can do if there are any very inquisitive potters in the chat or viewing today. You can do what's called local reduction. So you can put charcoal inside of a sealed container in an oxidation kiln and get local reduction, but that's a lot of work for something that you get naturally in a gas kiln. I've done it before because I didn't have access to a gas kiln, so it is kind of a fun project. But with a gas kiln, right, you can control the efficiency of the fire by how much you're introducing gas and how much oxygen you're allowing into the kiln. So usually you have your entry point for gas and your exit point for flame and fumes. And you can control how big that exit point is. So let's say I have a square and I have a piece of shelf, a piece of pottery shelf that's covering this hole in the top of the kiln. And the more I cover it, the less oxygen is getting into the kiln environment. And the less I cover it, the more oxygen is getting in. So that's how you're controlling, without having to change the flame at all, how much oxygen is getting in and how much fuel is able to escape. And so if I close it down, which you do during a period of intentional reduction, um, the flame would be the same. The environment starts to build up more and more fuel. And oftentimes you'll see a flame come out of the flue and out of the peep holes. Like I said, there are little holes that you kind of look into the kiln, and flames will come out of there because there's back pressure inside of the kiln. There's too much fuel. So the flame is reaching out to find more oxygen. And then the heavier the reduction is, right, the more fuel you have inside that's not being combusted efficiently, and eventually it'll actually crash the firing. So you'll get to a point where you have efficient firing is full oxidation, the flame has as much oxygen as it could want, and then you can kind of control how much reduction you have. But once you get to a heavy reduction, the way that you know you're in heavy reduction is that you've basically killed the progress of the firing and the temperature is now dropping. Mm-hmm. Mm-hmm. Exactly. Yeah, and iron is again the sort of most well known and most influential thing when we're talking about reduction in clay. There are other things in clay that interact with reduction, but really it's the iron that makes the biggest change. You go from something that can be quite light and bright in color to something very dark and sort of iridescent or metallic or even black, depending on how long and how thoroughly you reduce. Yeah. Hmm. Perfect. Hmm. So now we're talking about glazes. Before we're talking about clay and sort of the way that reduction interacts with clay. Now we're talking about glaze. So when you have oxides suspended in a glaze, right, you have a totally different effect than when they're trapped inside of a clay because there's really only so much mobility and so much interaction they can get. It's mostly on the surface. But with glazes, because they get totally molten and melted when they're firing, the atmosphere of the kiln kind of gets to interact with every layer of the glaze. So believe it or not, these are the same glaze and they're the same clay, right? The only difference being that one was exposed to reduction. And so the heavier melting power of iron in this glaze made it much smoother and shinier, and it turned it blue. Whereas this one, because it's sort of a higher fired glaze, one that wants more heat, when I fired it in oxidation, the iron has no action on it. The clay itself is not melting and incorporating with the glaze. So you end up with this frosty sort of white color. So really, really big difference. And this is a non-traditional celadon, but it is a celadon. And so in a similar way, a traditional celadon would turn yellow. This one is made with wood ash as the primary source of iron. And so it doesn't actually turn yellow, it turns that more clear or frosted white color in oxidation. But traditional celadons will turn yellow or sort of an ambery color in oxidation. And then when you apply reduction, right, you're pulling away the oxygen molecules from the iron in the celadon because it is actually iron that makes celadon blue. You get this blue color and a much shinier surface, which is well beloved in the pottery world and in the tea world. I certainly love celadons. I've been making and firing celadons since I started. And then some of the other ones are copper. So I actually did find an example. This sort of this blood red color. And because this is a copper glaze over porcelain, it looks a little bit different than what it would look on something else. And this wasn't a very thick application of glaze, so it just sort of looks like running red lines. But this is what copper looks like in reduction. It turns sort of a blood red color. And I'll touch more on that in just a second. this is what copper looks like in oxidation. So sort of blue-green, which is a lot more common to see, right, as a green color in ceramics versus a bright sort of blood red. But iron in reduction is very stable. So if you reduce the whole firing, and at the end of the firing, you want to fire a little bit hotter and clear the atmosphere, the glazes will remain the same, and so will the clay. But copper is very unstable, and it even will sort of aerosolize off of one pot onto another in a firing and cause little flashing spots on pots they're next to. And so if you fire copper in reduction, the full firing, but then you end with, or did I say that right? If you fire with reduction, the whole firing, and then you end with oxidation, you can actually re-oxidize the glaze and turn it from that red color back to clear or green. So it's really a tricky thing knowing your oxides, how they react to the environment, and what you can do during the firing to make sure you bring out the best in those glazes. And the last thing here is chrome. Mm-hmm. Mm-hmm. Yep. Mm-hmm. Yep. Yeah, and that actually, so it's similar deal. Iron, because it's much more resilient, much it's more stable, right? The iron in the clay is never going to go back to what it was. It's already fused everything together. It's already done its work to make the clay stronger. And so, yeah, you can fire the end of the firing in oxidation if you want to. I think we have a slide talking a little bit more about timing for reduction, but the last one for colors that I have experience with is chrome. And ooh, do I have an example? Yes, I do. So chrome in oxidation in an alkaline glaze is pink. And so when I fired this, I expected it to be pink, but obviously it's not. So when you fire chrome in reduction, it sort of removes the ability for it to turn pink or purplish, and you end up with this super bright grassy green instead. So this is actually, it's the same cup as what I usually put Celadon on. This is a white slip underneath, and then this is the base color of the clay. But you can see chrome is a really, really strong colorant. So this, believe it or not, what's that? Uh, Yeah, so the color would be just as bright and just as like sort of concentrated, except it would be pink, which is what I wanted. Yeah, I like brighter colors. Yeah, but this is a good sort of reference point, right? This is what it looks like underneath, and the chrome completely covers up really being able to see the clays. Whereas Celadon, right, because it's so nice and see-through, you get the full effect of what I was trying to do. So I ended up reformulating this glaze. This is only 1% chromium. So that's what 1% does. And I took it down to 0.5%, and I ended up with a really beautiful sort of green Celadon looking glaze. But yeah, so chrome turns pink in oxidation in an alkaline glaze, and then bright green in reduction, which I didn't actually know at the time. Mm-hmm. Mm-hmm. Hmm. Yeah. Yeah, and an important distinction, right, is if I'm talking about a glaze as being a certain type of glaze, it's because I've looked at historically how this glaze was developed. So celadons were developed particularly by mixing ground stone feldspar with wood ash, and the iron content in wood ash is what allowed it to turn these blue and green colors. So originally, way back in the day, ancient ceramics were made with just ground stone and wood ash was a main component in most glazes, and that's how you end up with these beautiful colors. And then depending on the type of wood that was burned, you get different color variations, which is why in Korea, for example, you have a much more green celadon glaze, whereas often in China you have the more pale blue sort of color. And yeah, that difference is both because of the wood and also because of the way that they were fired. But this is another really good example. So this is just the same clear glaze as this, right? Oxidation reduction. Mm-hmm. 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 Yeah. So when you talk about efficiencies versus inefficiencies, when you're talking about gas and reduction firing, that plays through into costs also, right? If you're firing in reduction, you're firing inefficiently. That means you're using more gas than can like efficiently burn. And so a lot of ceramic studios and a lot of big industrial companies that are making lots and lots of ceramics don't want to fire anything in reduction because it is inefficient, intentionally so, but it still is inefficient. And so most of the time when you're talking about modern glazing, they're using colorants that are going to be the same color powdered as they are when they're fired. And so you have a very consistent result. You know it's going to be the same every time. Whereas when you use oxides in reduction, you're going to have variation in every firing. And that's not what you want in an industrial setting. So like Dart said, you have things that are called celadon, but it's because they have the same color and sheen, but they're not actually following the traditional way that celadons are developed inside the fire. Mm-hmm. Sure. Mm-hmm. Mm-hmm. Yeah, I mean, this is exciting for me because it's just talking about like stylistic things with firing, which I'm very much into. I enjoy it a lot. So when you're taught in like a university setting or even in like a craft school setting here in the States, they're always going to talk about body reduction and glaze reduction. And that basically means that the rest of the firing, except for those two periods, they're doing a clear oxidation firing, right? As efficient as possible, climbing as quickly as possible, because the shorter the firing is, the more efficient you are with your fuel as well. And the more oxidizing you're doing, the faster it will fire. So you have these periods at around 900 to 1000 Celsius. I'm sorry, I'm just going to have to ask you guys to switch it back to Fahrenheit in your brains, but Celsius is much better for ceramics. So if you want to learn about ceramics, switch to Celsius on that. But from 900 C to 1000 C, or with pyrometric cones, which are temperature gauges inside of the kiln that bend at certain temperatures, it's cone O6 to O4. You'll put the kiln into reduction. So you'll close the damper and add more fuel and make sure that the environment inside the kiln is very turbulent and smoky and full of fuel so that it's pulling away the oxygen molecules from the clay. And the reason why we do it early is because this is just after when all of the organics have burned out of the clay. So you're less likely to have imperfections from that. And then it's also when the glaze is still a powder. So once the glaze gets to a certain temperature, it seals itself off. And then the clay underneath the glaze is no longer going to be able to be exposed to the atmosphere, right? It's being protected by the glaze. So this early reduction is done to expose all the clay throughout the vessel to reduction and make sure you get that more powerful, stronger melting inside the clay. And then the secondary reduction, once you get up to your final firing temperature. So for cone 6, which is done a lot in the States, that would be around 1200 degrees C, 1200 to 1250, depending on how slowly or quickly you're firing. And then cone 10 is more like 1300 C. And basically, once you hit that top temperature where you're done firing, you're then going to reduce again. And so you're going to reduce for an amount of time that you feel like is sufficient for what you're trying to achieve. If it's Celadon, you really don't need that much time, half an hour to an hour, if you've maintained a little bit of reduction. For copper, you want a pretty intense reduction. And so you're going to do a pretty strong reduction at the end of the firing to try to really brighten up that red color and get that bold sort of ox blood is what it's called, effect on the outside of the pot. And then the exact opposite is true out east. So in Taiwan or Korea or Japan, I'm not sure how they do things in China. I haven't been to a studio in China, so I can't say, but I know at least in Japan, Korea, Taiwan, mostly they just do a consistent reduction throughout the firing. So instead of clearing the atmosphere and having oxidation in between these two periods of reduction, it's just a consistent reduction all the way through after a certain point. So let's say after 600 C, when you've got most of your organics have burned out, then you're going ahead and firing with a mild reduction all the way up to where you want a final firing. And then you're just going to stop firing and let everything cool down. There are different stylistic things that you can do as well. Oftentimes in wood kilns, you'll do what's called a reduction cool. And that means that you're loading the whole firebox full of wood so that there's way too much wood that can possibly be efficiently combusted, but it's causing a really heavy reduction at the very end of the firing. And this is like, my hands are showing the flame going through the kiln. So you get a really heavy reduction firing going through, and that drops the temperature drastically compared to if you were trying to climb, but it actually makes it so that it goes more slowly down than if you had just clammed everything up and stopped the firing. So it basically allows you to reduce while cooling the kiln slower and controlled sort of that descent. So instead of it crashing, which it's still called a crash cool, but instead of just dropping off because you closed it, you're dropping it off with flame in the kiln, and you get all of the surfaces and all of the colors like copper locked in. And the slower cooling also causes a slight matting of the surface, so you don't get so super glossy, which is, you know, some people like super glossy. I don't particularly, so I do like a reduction cool. And you can do the same thing in a gas kiln, put it in heavy reduction at the end of the firing to get a sort of slow drop, crash cool. It's still called a crash cool. down versus a natural cool. So you're crashing it down with some reduction in order to get those sealed off surfaces, really get bright colors and a little bit of matting. Mm-hmm. Mm-hmm. Yeah. Yeah. Yeah, and that's I think we have a slide for that, but it's basically the difference in philosophy, right? Is that there we go. Yeah. So you're really focusing the kiln on what your result will be. So I do a mild or medium reduction throughout the entire firing. I also do like a heavier reduction when I first start after 1,000 or after 900 C in order to sort of lock in that body reduction, and then I do a crash reduction, but I do a reduction throughout the whole firing because I want to develop the surface. Because there are certain things like that metallic sheen that my clay can have that can really only be developed over time. If you did 2 spurts of reduction and that's all you did, you would never get that surface developing because it really has to interact with the clay for a long amount of time to get that sort of development. Whereas, in the US, most of the time we're just focused on firing and glazing and creating things that respond well to the firing process versus changing the firing process in order to get the result that we're looking for as a final result. So it's result first versus process first, and most of the time in the West we're going process first and then let's work with that process to see what we can do, versus in the East, and Japan is really a great example of that. Different firing techniques for every region in Japan, and each one is tailored to getting the best final result that you can get. So yep. Yeah. So basically, you have natural cooling, which means that you're just what I call clamming up. You clam up the kiln, you close all of the ports that go into the kiln, and make sure that it's as sealed as possible, so you can get a slow cooling as best as possible. Right. So that's a natural cool, and then you can do a crash cool, which basically means that you're leaving the kiln open, and that could be with flame or without flame, in order to get the temperature to drop from its peak down to a lower point, whatever that may be, right? There are certain points where you really don't want to go fast through temperatures, but for the first 100 to 200 degrees C, really you're safe as far as the structure of the clay. But it's a aesthetic and stylistic decision, right? If you're going to crash cool, it's because you want a certain effect. And the main two are that texture and the color. So if you get to your peak temperature and then you let it cool naturally, which just means you're cooling it as slowly as possible, you're closing everything up, and it's just sort of dropping naturally. What ends up happening is that the glaze and clay are still interacting with the surface and they're still staying hot. So glazes are more likely to run more. They're more likely to be very shiny because you've sort of just sealed off and you wait for the surface to do its thing slowly. So it slowly cools and becomes very shiny. Um, and then the other thing is that you can have the problem with copper where you get re-oxidizing. So you've got this beautiful surface that you've developed in this glaze. And like you said, with the clay, you really don't have to worry about it. You've developed it over the firing and it's safe. With glaze, though, oftentimes if you've reduced a lot and you've done all this work to develop surfaces, and then you just stop and let it cool naturally, you can get some sort of backpedaling of the glaze where it changes color, which you could want if you want a varied surface where sometimes it's red, sometimes it's clear. Because copper never really will turn green in reduction. It really goes clear or red. Um, but that's the idea, is that you're sort of sealing off the color when you drop that temperature, and you're giving it just that last little bit of interaction with the fire, and it allows the surface to sort of seal off and become a little bit more matted, and then it'll cool slowly after that point. So you only crash it down, 50 to 100 degrees C usually is what you're going to do. And then you let it cool slowly from that point forward. And that means that you can still get crystalline mattes. You can get, crystalline glazed surfaces because that can still